We're now going to take a look at another way of evaluating volumes of solids of revolution, and this method is called the shell method. Now sometimes, depending on the geometry of the problem, the shell method is going to be easier to use than the washer or disk method, or vice versa. Now note that the primary difference between the washer and shell method is that for the washer method, the axis you rotate it around is the same variable that you integrate with respect to. So for the washer and disk method, if you rotate around x, you integrate with respect to x. Or if you rotate around y, you integrate with respect to y. The shell method is the opposite of that. For the shell method, you integrate with respect to the other variable. So if you're rotating around the x-axis, you integrate with respect to y. Or if you rotate around the y-axis, you integrate with respect to x. So we'll see how that works out when we develop the shell method. So to start out in the development of the shell method, suppose we take a region R, as we have shown down here, and we revolve it around the y-axis to form a solid of revolution. So in this case, the solid of revolution would look something like this. And so that's roughly what our solid of revolution would look like when we rotate the shaded region R here about the y-axis. Now to calculate the volume of this, we're going to do something very similar to what we did with the disk and washer method, but just a slight variation of it. So down here, what we've done is we've taken the interval from A to B, and we've partitioned it into n subintervals. Now down here we have 1, 2, 3, 4. We actually have 5 subintervals. Now each of these intervals are going to be of width delta x. Right? So the distance from here to here is delta x, and that's b minus a divided by the number of partitions n that you have. Now what we're going to do is we're going to take each of these rectangular regions and rotate them around the y-axis, calculate the volume of those little shells that are going to be formed, add them up, and take the limit as n goes to infinity like we did for the disk and washer method. So if I take this rectangle right here, call that Ri, and I rotate it around the y-axis, what we get is something that looks like this. Now we want to calculate the volume of this shell. This is what we call a shell. So this is like a cylinder with a large hole cut through the center of it. And it has a certain thickness right here to it. And that thickness is this distance down here, which is delta x. So if you look at this cylinder or this shell from the top down, it would look something like this. So it would look something like this if you're looking from the top down. Now we want to calculate the volume of this. So what we're going to do is this. I'm not going to go through all of the algebraic details of calculating the volume of it, but I think you'll be able to see pretty easily what it is. Let's label this point right here, you see, right in the center of this interval. We'll call that point xi. And so that represents the distance from the center out to this point right here. It's in between the outer radius and the inner radius of the shell. So that distance is xi. Now if we were to take this shell and cut it along a seam like this and unroll it, it would form a rectangle with a certain thickness to it. So it would look something like this. So this is what it would look like if we were to cut it along the seam here and unroll it. Now, this distance from here to here, that's going to be f of xi. If this is our function right here, f of x, then this height right here is going to be f of xi. This distance, that's going to be the circumference around the circle that's in the middle, and so that's going to be pi times diameter, or 2 pi times xi, right? 2 times xi gives us the full diameter, so pi times diameter will be the circumference going around. And then the thickness of this slab right here is delta x. So this distance here, that is delta x. That's this distance right here. That is delta x. So then the volume, let's call it delta vi of this slab, well, it's just going to be length times width times the thickness. And so that's going to be right there we go. Now what we have to do is add up the volume of each of these shells. So if we take each of these gray rectangles and rotate them around and add up all of their volumes, we'll get a reasonably good approximation to the volume of the actual solid up here. So now what we have is this. So therefore the volume that we want, the volume of this solid right here, is going to be approximately the summation of all of these volumes down here. So it's going to go like this. And now you see, if we let n go to infinity, these rectangles down here will begin to perfectly fill in the true region R up here. They will become better and better approximations of the region R up here. And then we can replace the approximation with an equals. So our volume is actually then equal to the limit as n goes to infinity of this quantity right here, where each of these terms in here, that represents the volume of a little shell as we have pictured down here. Now, taking the limit as n goes to infinity here, recall that this portion right here will turn into an integral. Replace each xi with just an x and we get this. The delta x becomes a dx, and our limit of integration is from a to b. And there you go, we have the volume of the solid, and this is what we call the shell method. Notice that we rotated around the y-axis, but we integrated with respect to x because of the orientation of these little rectangles down here, because the thickness here, the delta x, is being measured along the x-axis. Now when you look at this formula, you should think of the x as measuring the radius of a shell. You see the x is like the distance from here out to that point right there, and that represents the radius of a shell. So the x is like a radius. And the f of x right here, that really is measuring the height of your shell right here. This distance is f of x. In this picture, it's actually f of xi. And so you should think of the f of x as being the height of each shell. And this formula right here is what we call the shell method for rotation around the y-axis. Now we have this formula summarized below, and we'll see that we also have a corresponding formula for rotation around the x-axis, except then we'll be integrating with respect to y for the shell method. So here's the result that we just developed. If you're given a continuous, non-negative function y equals f of x, defined on some interval a to b, where a is greater than or equal to 0 and b is greater than a, then the volume of the solid generated by revolving the region R, which is the region bounded between the x-axis and the graph of the function for x between a and b, the volume of the solid generated by revolving that region about the y-axis is given by this formula. Now, when you look at this formula, you should realize in the development of it that the x represents the radius of a small shell generated by rotating a rectangle around the y-axis. So this represents the radius of a shell. We saw that in the development of this formula. The f of x should be thought of as the height of that shell, and the dx is the small thickness of the shell. So when you multiply these terms together, that gives you the volume of a very thin shell generated by rotating a rectangular region around the y-axis. That's what you should think of when you see these. And remember the integral. Actually, that sort of represents a summation. Now, depending on the geometry of the problem, the x and the f of x will change depending on the axis of rotation and what your region looks like. So down here we have a more general form for the shell method, and this is for rotation about an axis parallel to the y-axis. So you notice we replace the x with some general function we denote as the radius of x, so this is just some function, and the f of x we replace with the general height of x function. Now, to motivate this, to see why the x and the f of x can change, take a look at this graphic that we have over here. So suppose we take this region that we have labeled here R, which is the region bounded between the graph of two functions f of x and g of x for x between a and b, and we take this region and rotate it around the line x equals negative c, which is an axis parallel to the y-axis. Now notice that this thin rectangle that we have drawn here will generate a shell as we have pictured down here when it is rotated around the line x equals negative c. Now, to calculate the volume of this shell, it's going to be 2 pi times the radius of the shell times the height of the shell times the thickness of the shell. Okay, so we need to calculate the radius of this shell and the height of the shell. All right, well, notice that the radius of the shell is going to be this distance, and that distance is x plus this distance, which is c, right? If c is negative 3, for example, this distance would be 3 plus the distance from here to here, which is x. So this distance is going to be x plus c, and so that's the radius of the shell. So right here we have the radius of the shell. Now the height of the shell is going to be y1 minus y2, and y1 is equal to f of x and y2 is equal to g of x, and so this term right here is going to be the height of our shell. And then the thickness of the shell is this distance right here, which is we denote as delta x. And so here's the volume of the shell generated by rotating this rectangle around the line x equals negative c. 2 pi times x plus c times f of x minus g of x times delta x. And so if we integrate this, the delta x will become a dx, and we'll get the volume of the entire solid as we integrate from A to B. And so notice that the x becomes an x plus c, the f of x becomes a f of x minus g of x, and so that's what we're referring to over here. So in this case, the radius of x, that's the x plus c right over here, and the height is the f of x minus g of x. And then you still have your dx. And that's how these terms here can change depending on the axis of rotation and how the region R is defined. Now if you revolve a region R around an axis parallel to the x-axis, well then this formula remains basically the same, except everything becomes a function of y now. So the radius becomes a radius as a function of y, the height becomes a height as a function of y, and then you're integrating with respect to y instead of x. And your limits of integration would be c to d, and then you multiply by 2 pi, of course. So this is for rotation around a line or axis parallel to the x-axis. And before we look at some examples, let's note one other thing. These two formulas that we have here, these are both referred to as our shell methods. And keep in mind, for the shell method, if you revolve a region parallel to a given axis, then you integrate with respect to the other axis variable. So for example, if you rotate around a line parallel to the y-axis, you integrate with respect to x. And that's in contrast to the washer or disk method, where if you rotate around the x-axis, you integrate with respect to x, or if you rotate around the y-axis, you integrate with respect to y. Now let's take a look at some examples. So here we want to use the shell method to find the volume of the solid when this region bounded by y equals x squared, the x-axis, and the line x equals 2 is rotated around the x-axis, the line y equals -1, the y-axis, and then the line x equals 3. So let's start with rotation around the x-axis first. So we're going to rotate around this axis. Now the region is this region right here, R. You notice that this curve right here, that's y equals x squared. Of course we have the x-axis down here, and then the line x equals 2. So this is 2 right here on the x-axis, and up here on the y-axis over here we have 4. So let's use the shell method here. Now notice we could use the washer or disk method here, but we're going to use the shell method. Now once again, for the shell method, I think it's easiest if you draw a line or a very thin rectangle. Now, however, for the shell method, it is going to be parallel to your axis of rotation instead of perpendicular like for the disk or washer method. And so now we have to calculate the radius of this shell and the width of this shell. Alright, so what we want to do is let's label some points here. So let's label these 2 points like we did before. That point right there we will label as, let's see, the x-coordinate is always 2. And the y-coordinate, we'll call that y. And over here, that point right there, let's just label that as x, comma, y. Now, following the formula for the shell method, our volume, 2 pi, integral. Now we have to calculate the radius of this shell times the width of the shell. Now let's see. The radius of the shell is going to be this distance. That's the radius of this shell. Now that distance is y. You see, we read that from the y coordinate of these points. So we just put in a y right here. So that's the radius. Now the width of the shell, this distance, well, let's see, that point is x on the x-axis, and if I drop down here, that is 2 on the x-axis. So this is the width or height of the shell, and that is going to be 2 minus x. Okay, so times 2 minus x. Now we're rotating around the x-axis, so we have to integrate with respect to y. So this is going to be a dy right here. And you can also see that if you look at this little rectangle that we drew, it has a little thickness right there, dy. And that's because this is being measured with respect to the y-axis. Okay, so that's a little thickness dy right there for that shell that's being formed. And let's see, what are the limits of integration? Okay, so we're integrating with respect to y, so like right there is y on the y-axis. So it looks like we're going to go from 0, the x-axis, or the x-axis, that's when y is equal to 0, up to 4. That's what the y can vary from. That 4 we get from putting 2 into x squared. So 0 to 4. Now we want to integrate with respect to y, so of course we need everything in here to be in terms of y, so we need to rewrite x in terms of y. Well, you notice that the x came from here. That point lies on this curve, and that is the curve y equals x squared, or x equals the square root of y. So there you go. We just have to put the square root of y right in here for x, and then we can finish the problem. And there we go. Now you just have to integrate that. So we'll find a numeric answer for this one, and then the other ones we'll just set up the integral and you can evaluate them. So this is going to be 2 pi 0 to 4 of 2y. Now y times root y is y to the 3/2. Antiderivative of 2y is y squared. Y to the 3/2. I add 1 here, I get y to the 5/2. And I have to multiply by 2/5 out here to counteract the 5/2 if I were to differentiate by dropping this down. So the 2/5 would cancel, and I would get back a 1, which is right there. And then we need to evaluate that from 0 to 4, and we get all of this right here will evaluate out to 16/5. And so we're getting 32/5 pi. And there you go. That's our answer for rotating this region around the x-axis. Notice we could have done this with the disk method as well. Now let's take a look at part B. So now we want to rotate this region around the line y equals -1. So let's see how we set that up. So the line y equals -1, that's right down here. So now we want to rotate around that line instead of the x-axis. Now notice this line is parallel to the x-axis, so we're still going to be integrating with respect to y. So our volume, 2 pi. Okay, so now what we need is the radius of our shell. That goes first. So the radius, I'll write it like this, radius times the height, dy. Now the radius is going to be the distance from your axis of rotation to your shell. Alright, so this distance right here, this distance, label it right there, that's going to be, you see this is a y, this distance is y plus 1. So that's y plus 1. That's going to be the radius of the shell that forms when we wrap this around this line. So our radius is y plus 1. See that? Once again, these points here, the y coordinate is y for each of them. So that's the distance from here to here, and then I have to add 1 to it. The height or width of this shell is still 2 minus x. That's this distance, 2 minus x dy, and the y still goes from 0 to 4. And then once again we just need to rewrite the x in terms of y. Well, we already did that last time. And so this is going to be and there you go. Notice everything in here is now in terms of y. So you can FOIL this out and integrate everything pretty easily. And then just evaluate from 0 to 4, multiply by 2 pi, and you'll get your answer. Once again, also notice we changed the x into root y because the x comma y lies on the curve. This point right here lies on the curve y equals x squared, or x equals the square root of y. Now let's take a look at this should be part C right here, and then D right here. So now let's rotate this region around the y-axis instead. So we're going to have to redo our picture here. So now we want to rotate here around the y-axis. So now what we're going to do is, to start, let's once again draw a little thin rectangle, but now it's going to be parallel to our axis of rotation. Okay, so for the shell method, we draw it parallel to the axis of rotation. Let's label some points here so we'll be able to pull off the radius and the height of this little shell. So that point right there we'll label as x comma 0. Okay, see that's x right there on the x-axis, and the y-coordinate is 0. This point right here we will label as x comma y. And notice that the x here can vary from 0 out to 2 again. And we're all set up now. So let's write this out as volume is going to be, by the shell method, 2 pi. Now we need the radius of our shell. Okay, so the radius is going to be this distance, and that's just x. You see that's x right there on the x-axis. Now the width of the shell is this distance. So you see this distance, this point right here is x comma y, so that's y right there on the y-axis, and so that's going to be your exact height or width of your shell. So times y. And the thickness here is a dx. That's this distance right here. Notice that that's being measured with respect to the x-axis. So dx, and then the x can vary from 0 to 2. We put 0, 2 because we're integrating with respect to x. Now we just have to change the y, rewrite the y in terms of x. Well, this y came from here, and that point lies on, this point right here lies on this curve, which is y equals x squared. So we just need to put an x squared right in there for that y, and we're finished. And there you go. This, of course, being x cubed. And that's pretty easy to evaluate. And there you go. There's our answer. Now let's take a look at rotating this around the line x equals 3. So now we're going to rotate around that line, this region here. So it's still going to be the same setup. Volume is going to be 2 pi. Now we need the radius times the height of our shell. Alright, so this is going to be our shell. That's going to form our shell. So the radius is the distance. It's going to be this distance. That's the radius of our shell. Now this point right here is 3. That's the line, x equals 3. So this distance is going to be 3 minus x. You see x is right there. That's x on the x-axis. So this distance is going to be 3 minus x. So 3 minus x times, and now we need the width of the shell or height of the shell. So that's this distance right here, that distance. And we see that's just y still. And then we're integrating with respect to x. This axis is parallel to the y-axis. So for the shell method, if we rotate around an axis parallel to the y, we integrate with respect to the other variable, which is x in this case. And you can also see that thickness right there is a dx. And the x still varies from 0 to 2. Don't be tricked. It doesn't vary from 0 to 3. It only goes from 0 to 2. This x right here varies from here to here. It doesn't go up to 3. So 0 to 2 yet. And then, of course, we need to replace what y is. Well, that y came from this point right here. And that point sits on the curve y equals x squared. So the relationship between x and y is, well, y equals x squared. So I replace this with an x squared. And there we go. And that's it. Everything's in terms of x. We can integrate this with respect to x, no problem, and we'll get our answer. This one's pretty easy. I may as well do that. And there you go, that's our answer. That just happens to be equal to one of our other answers we worked through up here, but that's just a coincidence. And so that concludes our discussion of the shell method.